Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare. This is my continuing feature on the Math Lovers book, three-volume series I wrote from 2019 to 2022. It's available on Amazon, both Kindle and paperback formats, in case you're interested in purchasing any one of these volumes or all three if you like. But today I'm going to continue what I started talking about yesterday, namely truth tables, which is a very useful construction in Boolean algebra for analyzing various types of Boolean expressions. So anyway, let's begin. So yeah, last time I just gave the truth tables for the basic, or for six different Boolean operators, which we're going to use a fair amount. I think I did and, or, not, and then three a little bit more complicated ones, if then, equivalence, or if and only if, and exclusive or. But we don't have to do it for just familiar, unary or binary logical operators. We can do it for arbitrary Boolean expressions or Boolean functions, if you like. So, for instance, I'm going to do three examples. That's all I'm going to do today. I'm going to present some examples of some sort of complicated Boolean functions. The first two involve three variables. The last one involves four variables. And I think I mentioned yesterday that if you have a Boolean function of n variables, there's 2 to the n rows of the truth tables. So the truth tables get big very quickly, but you very rarely see more than 4. So anyway, here I'm starting with an example involving three Boolean variables, which I'm calling P, Q, and R. And since there's three Boolean variables, there's a total of 2 cubed or 8 possible values for every combination of P, Q, and R, and they're all listed in this truth table. So that's always the first thing you do. If you want to analyze the truth value of a given Boolean expression in n variables, the first thing you have to do is write down the names of all the n variables and then the truth values of all of them. And you have to use every possible combination. The way you can do that, or you can just think of this as kind of like listing binary numbers. If we used 0 and 1 instead of T and F, it would go 0, 0, 0, 0, 0, 1, 0, 1, 0. It's like you're counting in binary, but you're just using T and F instead. So that's how you get the values on the left. And then to get the value of P and the parentheses are important here, by the way. And and or don't commute with each other. So we have the expression P and then Q or R in parentheses. That means you first do Q or R and then you do P and that. So that's how you analyze this. You kind of break it down. So Q or R is easy. I mean, we did that last time. Q or R is true if and only if either Q is true or R is true. And I think you can see that there's 6 out of 8 possibilities for that. The only cases in which Q or R is false is if both Q and R are false, and P doesn't. These don't care about P, so P could be either true or false. So those are the two false cases. P true, Q and R both false. That's the fourth row. Or P false, and Q and R are also both false. That's the 8th row, or the last row, if you like. All the other rows are Q or R is true. So that gives you the first kind of derived column. And then to get P and Q or R, you just take the conjunction with P. So you look at the columns P now and the column Q or R, which we just made. And we know that P and Q or R is true if and only if they're both true. And I think you can see from these two columns that the only cases in which they're both true are the first 3 rows, namely P true. So in all those cases, both P and Q or R are both true. So P and parentheses Q or R are true. But now in each of the other 5 cases, you'll notice that, for instance, in the 4th case, P is true, but Q or R is false. that makes P and Q or R false. Only you need one of these to be false. And then for the 5th through the 8th rows, I think you can see P is false for all of those. And we don't really care about what Q or R is in those cases because false and anything is false. So that gives you the truth values. This is the truth table of the logical function P and parentheses Q or R. So I think you get the idea how to do this. But I'll just do a couple more examples. How about this one's a little more complicated because it involves a more complicated Boolean operator, namely equivalence. It's not really much more complicated though. So again, we have a function of 3 variables, P, Q, and R, and we list them on the left the same way we did for the last example. And then in the first derived column, we have Q is equivalent to R. And if you remember from yesterday, two Boolean statements, two atomic statements are equivalent if and only if they're either both true or they're both false. And so you can see, you just look at where the columns for Q and R on the left, and we see when they're both either both true or both false. And you can see in the first row, they're both true. So Q is equivalent to R is true in that case. And in the 4th row, they're both false. So Q equivalent to R in that case as well. But it's false in the 2nd and 3rd because they're different. Q is true and R is false. And in the 3rd row, Q is false and R is true. And you'll notice that the 5th through 8th rows are just a repeat as far as Q and R are concerned of the 1st through 4th rows, because the only thing that's changed here is P. P has gone from Q to false, but we don't care about that for the 4th column here because that doesn't include P. So you're going to get the same, is that right? Yeah, I think I made a mistake here. Yeah, the 5th one should be true. I made a mistake in my book, which is very rare. I double check pretty much everything in the book, but this should be true, false, false, true, true, false, false, true. So I made a mistake. But the mistake kind of goes away in the last column. So now we want to do the conjunction of Q is equivalent to R with P. And you'll notice that for the first 4 rows, P is true. That means that we can ignore P as far as Q is equivalent to R goes, because true and anything is just the second thing. So, for instance, if P is in the first row, P is true and Q or R. Q is equivalent to R is also true. That means P and Q is equivalent to R is true. And you can check the remaining 3 cases. The 4th case is like that case. 2nd and 3rd, P is true, but Q is not equivalent to R, so those 2 cases are false. And then for the 5th case, which I messed up in this picture, P should be false now and Q equivalent to R is true. But as far as conjunction goes, it doesn't matter because P is false. That means the conjunction is false. So for the 5th through 8th cases, I think you can see that P and Q is equivalent to R are all false. So this is the truth table for that Boolean expression. I'm going to do one more example. This is the most complicated one I'm going to give. And I hope you guys can see this. If you're using your smartphone, you probably can't. But if you're on a computer, you might be able to see this truth table here. It's got 16 rows. It's got 4 variables this time, which I'm calling P, Q, R, and S. And so we have to go through all 2 to the 4th or 16 possibilities. It's a lot of possibilities. Like I said, these things can get to be kind of a pain when the number of variables gets large. But anyway, let's just go through this. So the Boolean expression we want to come up with a truth table for here is it's the disjunction of 2 conjunctions. So our first conjunction is P and Q. So we have P and Q in parentheses, and then we have OR, and then we have R and S in parentheses. So we want to know the truth values for this complicated Boolean expression. And like we did in the other 2 examples, we break it down first. So we first have to have a column for P and Q and another column for R and S. And you could go through all the possible cases, and I don't think I want to do this. It's going to be kind of a pain. But P and Q just suffices to say that P and Q is true if and only if both P and Q are true, which is the case for the first the first four rows. So notice that in the first four rows of this truth table, if you look at the two columns on the left, P and Q, they're both true in all four of those cases. That means that P and Q is going to be true for all those four cases. What about R and S? Well, R and S, it looks like that's true in both cases for the first, fifth, ninth, and 13th rows. So, and then all the other cases are going to be false. So that's what we get for R and S. R and S is true in the first, fifth, ninth, and 13th cases, and it's false in every other case. And now finally, we want to do the disjunction of these last two columns we've written down. So that, remember, disjunction is true if and only if at least one of them is true. So remember I said for the first four rows, P and Q is true. That means that the disjunction is true. So P and Q or R and S is true for the first four rows. It's also true for the fifth, ninth, and 13th rows. For all those other cases, P and Q is false. But disjunctions don't care about one side being false. They only care about the other side. And as long as the second side's true for those cases, then P and Q or R and S is true. So that's true for the 5th, 9th, and 13th rows, but it's false for all the other ones. So that's the truth table for P and Q or R and S. So you can always do them like this. If you break them down, if you just build up the Boolean expression one step at a time. And if you do that, you can construct a truth table for any Boolean function you want. But like I said, it's very cumbersome if you have more than about 4 Boolean variables. But anyway, that's how you do that. And we're going to use truth tables some more. I mean, right now I've just kind of talked about the mechanics of how to make truth tables. But next time I'm going to talk about tautologies and contradictions, which are an important class of Boolean expressions. A tautology is one where it's always true in every possible case. And a contradiction is one where it's always false. Anyway, we'll go over that next time. But that completes my video for today. Thank you for watching. Long live math. And I'll see you guys next time. Bye.